In this video, we're going to look at how to calculate the probabilities of type 1 and type 2 errors for a two-tailed Poisson distribution hypothesis test using the TI-Nspire calculator. As a quick review, a type 1 error is when you reject the null hypothesis, even though it's true, because your sample fell for some reason in the rejection region. A type 2 error is when you keep the null hypothesis even though it's false, even though the alternate is true, because your sample, for some reason, fell into the acceptance region. In a previous video, I talked about calculating type 1 and type 2 errors for normal distribution, Z or T tests, and I explained why the probability of a type 1 error is equal to alpha for a normal distribution. But for binomial and Poisson, that is not the case. Your probability of a type 1 error is still equal to the probability your sample fell into the critical region, given that your H null is true. But for Poisson and binomial, because they are discrete distributions, let's say you're doing a lower tail test, your alpha of, let's say it's 5%, may not fall perfectly on a sample value on a particular outcome. And so if your critical region is, say, 1 or fewer, and the probability of 1 or fewer is 3%, then you are actually using 3% as your alpha, not 5%. And so your p-value, the probability of a type 1 error is for your sample to fall in this region, which is 3%. So on the TI-Nspire, we're going to find the critical region, which will eventually be our lower and upper bounds, by first in a calculator defining a Poisson CDF and then creating a table from a spreadsheet to look up all the possible p-values and identify where your critical value is. If you have a lower tail test, then in this calculation for a type 1 error, you would have your null hypothesis claim for your lambda. Your lower bound would be 0 and your upper bound would be the critical value. If, however, you're doing an upper tail test, then your critical value is your lower bound, and some big value compared to lambda is going to be your upper bound, and that's because a Poisson distribution goes forever, technically. And so I just my rule of thumb is take the lambda and multiply it by 100 or 1,000, and that'll be a big enough number. For calculating the probability of a type 2 error, we in IB math are going to find the probability that the sample fell into the acceptance region. And so that's going to be the complement essentially of your critical region. And we're going to be using a value given in the problem for the true lambda, the true mean rate of this distribution. And so the wording might be something like, further testing revealed that the true value of lambda is such and such, or unbeknownst to you, the true value of lambda is this. And so that is what you would put in for lambda on this Poisson CDF. If you are doing a lower tail test where your critical value is the upper bound and the lower bound is 0, in this situation here, then your acceptance region is going to be the reverse. You'll have a critical value here, and then some big number would be your upper bound. Flip all that around, though, if you were doing an upper tail test, like in this situation, then your critical value for type 1 will be your lower bound, big number for upper bound, and then 0 is your lower bound for the acceptance region, and critical value is your upper bound for the acceptance region. Let's look at an example. Historically, your patio had only about 3 bees visit per day. Now that you've planted tulips, you want to see if that frequency has changed. As you sit and enjoy your daily afternoon tea, you count how many bees you observe during that hour each day, and you do that for 5 days. Let X be the number of bees seen in an hour over the 5-day period, and the level of significance used is 10%, which means your alpha is going to be 0.10. Now, I want to point out here that for Poisson distributions, you need to take a look at your lambda units. So this is 3 B's per day, but your sample is over 5 days. And you always want to convert your given lambda units to match your sample. And so what we're going to do here is we're going to take 3 B's per day and multiply that by 5 days are in a 5-day period. So I kind of write it out. So I can cancel out the units of days. And now I'm left with 3 B's times 5 over a 5-day period. Or I should see, on average, I should see 15 B's for every 5-day period that I'm looking at. So my null hypothesis is I should see 15 B's over that time. And my alternate is just not equal to 15 B's over that time. I'm doing a two-tailed test, so I'm interested in whether or not there's less bees visiting. Maybe they don't like tulips, or maybe more bees visiting because they do really like tulips. So we're going to do a two-tailed test here, which is going to make this a little bit more challenging. Part A, find the probability of a type 1 error. So we want to find the probability that your sample is in the critical region given lambda equals 15 B's per 5 days. So what we're going to need to do first is find both critical regions. There's going to be a lower tail critical region and an upper tail critical region. We're going to start by defining 2 functions in a calculator page using a Poisson CDF. Then we're going to move those functions over into a spreadsheet and convert it into a table. By doing this, what we're actually doing is asking the calculator to calculate a PDF at 0 or less, 1 B or fewer, 2 B's or fewer, 3 B's or fewer, etc. So we're getting a bunch of CDFs, and that lower bound is fixed at 0, upper bound is changing, so it's a variable. And so when I do the lower bound critical region, I'm going to enter my null lambda, lower bound is 0, and my upper bound is changing, so we call that X. The upper tail, again, we're going to use the null lambda, and now I'm looking at changing upper bound. So I'm going to do a infinite number of B's and then keep doing a CDF on down, and so that lower bound is what's changing. And so we're going to use lower bound for X, and I use any really big number because in a Poisson distribution this can go forever. And my rule of thumb is I take my lambda, multiply it by 100 or 1,000, and that'll do the trick. So you define those, then you make a table, and you look in your table for your 2 critical regions. Since we have an alpha of 10%, 5% has to be on this side, and 5% will be on the other side. So I'm looking for 5% in my tables. I can see that 5% is right in the middle here, and then it gets lower. And this is my lower critical region. So it's right between 8 and 9 B's per 5-day period. And so I would write that critical region is X, my variable, B's per 5-day period, is less than or equal to 8. And then the upper critical region, we can see here, is right between 22 and 23 B's. And if I keep going bigger, I get smaller and smaller probabilities. So I would say that this upper critical region is X is greater than or equal to 23 B's per 5-day period. So there's my 8, there's my critical region there, and 23 is somewhere in there. And so that's a critical region. We've got all that down there and all that up there. And that means that my acceptance region is 9 up to 22, and that will be the acceptance region. And I'm going to use that in part B for calculating a type 2 error. Back to the type 1, we're finding the probability that X is in this critical region. Well, there are 2 critical regions, so I need to do 2 different Poisson CDFs, one looking at the lower critical region and one looking at the upper critical region, both under the condition that your null hypothesis is true. Oh, that is actually a typo. It should say 15. Both of those should say 15. When you type those into your calculator to just calculate a general Poisson CDF, we have our null lambda. Lower bound is 0, upper bound is 8. And so we get a probability of about 3.7% right there. Then for the upper critical region, we have our null lambda. Lower bound is 23, upper bound is anything big. And that probability comes out to about 3.3%. Since there are two regions, we actually want to add them together, because if you just think about probabilities, we could be in this region or this region, and or means add up. So we add those up, and so the probability of a type 1 error is going to be about 7.02%. Now, if you want to reduce the probability of a type 1 error, you need to use a smaller alpha. Now, an alpha of 10% broken up in half means you've got 5 and 5. That's already made smaller because we're not really using 5%. So you might want to say, if your alpha is, change your alpha to saying like 5% alpha, then you'd be looking for 2.5 and 2.5%, and that would reduce your probability of a type 1 error. Part B, unbeknownst to you, the true value of the rate, average rate, is 10 bees per day. Find the probability of a type 2 error. So again, make note of the units that they're using, and remember that your sample is using 5 days. So you'd multiply this by 5. So your rate should be 50 bees per 5-day period when we're doing this calculation. The probability of a type 2 error is the probability that your sample, how many bees you counted over 5 days, fell into the acceptance region, given that you actually have a different lambda here. And that acceptance region is between 9 and 22 bees. And when you type that into the calculator, you can see I made some silly mistakes here, but you're going to enter the alternate lambda given in the problem. Your acceptance region is right there. And this probability of a type 2 error is very, very tiny, 0.0007%. And if you wanted to reduce that even further, what you would do is use a larger sample size, so a larger N. That's what you would do to reduce that probability of a type 2 error, increase your sample size. Let's take a look at how to do this in the calculator. Okay, on your TI-Nspire, you're going to start with a new calculator document. We can't use a scratch pad because we're going to eventually need to use both calculator and spreadsheet in the same document. So start with calculator, page. We are going to find the critical regions, so I'm going to define a function. I'll start by naming the first function f1 of x. And I define it by doing control and the number, this button that's next to the 9, that's the definition button. And then we're going to do a Poisson CDF. So I'm going to go probability or stats, distributions. At the very end of the list here is the Poisson CDF. The null lambda is what we're starting with to find the critical region, so 15. And to find the lower bound, the lower tail, because there's two tails, we're going to have lower bound of 0, upper bound of x, hit OK. But I need to also find an upper critical region. So I'm going to do the same thing. I'm going to go f2 of x, control, and this button next to 9 to define it. We're going to go menu, probability or stats, all the way down to the bottom of the list for Poisson CDF. 15 bees per 5-day period. Lower bound is now x, and upper bound is any really big number. So what my rule of thumb is, take the lambda, multiply it by 100. So 150 bees in a 5-day period would be a lot, and that'll cover the basis for us. When they both say done, we can now do control doc to add a page, and we're going to add a list and spreadsheet. I want to change this spreadsheet to a table by doing control T. So F1 will give me my lower critical region. Click in the next column. F2 will give me my upper critical region. So I want to look through, well, first off, these are all the CDF outcomes. So you could get 1 or fewer, 2 or fewer, 3 or fewer. For column 1, this would be 1 or more, 2 or more, 3 or more, depending on which column you're looking at. Column 2 and 3 are the p-values that go with those CDFs. So these are all really small. I need to go up until I see 5%. And there it is, right between 8 and 9 is 5%. So 8 is smaller than 5%, 9 isn't. So 8 is my critical value. This is then getting smaller going towards 0. So my lower critical region is 8 or smaller Bs per 5-day period. To find the upper critical region, we're going to keep going down until we get to smaller than 5%. And there it is. So 23 or more Bs in a 5-day period is my critical region because this p-value is smaller than 5. 22 is in the acceptance region because it's bigger than 5%. So I now know that my critical region, there's 2 of them, and I know my acceptance region. I'm now going to calculate those PDFs. So we'll do menu, probability or stats, distributions, Poisson CDF, and the lambda, the null hypothesis is 15. Let's find the probability first of the lower tail. And so this is 8 or fewer Bs. And then we'll do the same thing. I'm going to just arrow up and copy all that. Control C. And right here, I will do Control V to paste it. And I'm now going to change my bounds. So this will be, the upper critical region was 23 or larger. So we'll do comma, some really big number, 150 will do the trick, hit enter. So if I want the probability of falling in the critical region, I need to add these 2 tail probabilities together. I'm just going to use my arrows up, Control C, copy that value, Control V, paste it down. Then I'm going to do plus, and I now want to take the most recent answer. So I'm going to go Control, and this button next to the enter sign has an answer. That's going to pull that one there. I'm going to hit enter, and it's added those 2 probabilities together to get a total probability of about 7%. That is the probability of a type 1 error. Probability of a type 2 error, we're going to use, again, a Poisson CDF. Distributions, Poisson CDF. We need to use the null, or not the null, the alternate value that was given, the true value of lambda, after we've multiplied it by a 5-day period. So we had 50 Bs in a 5-day period. And the acceptance region is what we now want to enter for lower and upper bounds. So acceptance region was 9 up to 22 Bs. And that is the probability of a type 2 error. So it's super, super tiny. If you get 50 Bs in a 5-day period, you actually have a very low chance of having a type 2 error. Of course, you don't know that unless someone actually tells you what this true value is.